electrons and why are they so important in chemistry? Valence electrons, remember, those that are farthest away from the nucleus at the highest energy level, and that valence electrons are those parts of the atom which dictate the atom's chemistry. How does it behave chemically? Comes from its valence electrons. Okay, so those chemical properties of the atom are basically a function of its valence electrons. Number two, how many valence electrons are in the following electron configuration? I know we did this one, but as you look at it, how are you going to determine how many valence there are? What's your process when you see the full electron configuration? Yes?
You count the number of natural bills, but you don't count.
First thing I want you to do is look at the energy levels. Do you remember what the energy levels are when you look at that electron configuration? How do you know the energy level? It's the Arabic numbers, like 1, 2, 3, 4, 5, right? The large ones in front of the letters. That's your energy level. So as you look at this full electron configuration, you see first, second, third, fourth, and fifth energy levels. Okay, because, for example, the fourth energy level contains the 4s2, the 4p6, and the 4d10. Right? So you look at the highest energy level. What's the highest energy level on this configuration? The fifth energy level. Okay. How many valence electrons are in the fifth energy level?
5.
Okay, so you've got the 5s2 and the 5p3. What is this element? This valence electron is a 5p3 electron. 5p 1, 2, 3. Okay. So its fifth energy level has a 5s2, 5p3 for a total of 5 valence electrons. Number 3, this is a question about silicon again. Talks about how it's speculated that, you know, of all the elements, that possibly silicon could be another form of life. We have carbon-based life, which is what we're used to. All of our life forms are carbon-based that we're familiar with. Some scientists speculate that there could be a silicon-based life form. And what's the principle why they assume that silicon would be the next likely candidate to be a basis of life after carbon? Behaves so much like carbon. Specifically, it's a column 4 element. It's one, so it has the same number of attachment points. So remember when we talk about how molecules are formed with electrons and the other ions around it, or the other elements that form, that carbon and silicon have the same number of attachment points. They have 4 individual electrons, so they can bond the most things to them in that way. They're very close together in terms of electronegativity and ionization energy and radius, the same chemistry basically. So there's a speculation that if there is another form of life, and, you know, there could be lots of different forms of life, hypothetically, but that we can relate to because we are carbon-based, the next likely would be a silicon-based, because the similarity between carbon and silicon. Number 4, what are the noble gases and why are they important? The noble gases are located on the periodic table at the column 8, all the way over here. And they're significant because their octets are full, right? They're inert gases as well. So they're non-reactive. They don't want to react. But they have the ideal electron configuration. They are set. They don't have to get any or give any to get their octets. What is the octet rule? Okay, so we're talking about getting 8 valence electrons. You said you started with they all. Okay. Mostly all, right? There are some exceptions. Mostly all. So just because an element doesn't want 2 doesn't mean it's not trying to satisfy the octet. Mentioned hydrogen in the last video we saw. Hydrogen can only carry 2 in its 1s orbital, right? 1s2, 2s2. Then we get, excuse me, 1s1, 1s2, 2s1, 2s2. And so we do have some exceptions that are only looking for 2 electrons in their highest energy level, but the vast majority want 8. So if you see something that says hydrogen wants to have 2 electrons, does that complete its octet rule? Yes, it does. The octet rule is a generalization. Most elements want 8 A few exceptions want to. What is the fundamental difference between metals and nonmetals? Go ahead. Right, metals are giving up electrons. Nonmetals want to receive electrons, gain electrons, right? So metals are trying to give electrons away to reduce down to their valence, reduce down to their octet. Nonmetals are trying to gain electrons to build up to a full octet. Critique this statement. The number at the top of a column on the periodic table is the number of valence electrons that all elements have. Now, I think that could have been worded a little bit better. What I think they're asking is that the number on top of the column indicate all the valence electrons in that column that they have. But is that still true or false? It's false. It's true for all of the column A elements. 1A, 2A, 3, 4, 5, 6, 7, and 8. It's true for those. It's not true for the B columns. 3B, 4B, 5B. The number at the top does not indicate how many valence electrons they have. Right? It's only true for the column A column elements. 1 through 8A. Not the B columns. What's the difference between an atom and an ion? Yes, Will? You said, what is the difference between? Give me more information. What is the difference between an atom and an ion? Just what you said, but give me more information. What is? An ion is an atom which has gained or lost electrons, right? Okay. So, I'm sorry, I couldn't work with two partial answers. So an ion is an atom that has gained or lost an electron. That doesn't mean an ion is not an atom. What it's saying is a neutral atom has the same number of electrons as it has protons. An ion is an atom which has more or less electrons than it has protons. And because it has more or less electrons, it now has a net charge. When the atom has a net charge, it is an ion. When the atom has a net positive charge, it is a cation. It's a metal, usually. And whenever an atom has a net negative charge, it's an anion. It has more electrons than protons. Okay? All right. So an atom generally is thought of as the same number of protons as electrons. An ion has an imbalance, has more or less electrons than protons. What is the ionization energy? Ionization energy and electronegativity are two of the three periodic properties, right? Ionization energy and electronegativity are communicating the same kind of an idea, but from slightly different perspectives. Yes, Will? Correct. It's what, but one way to think of it is how much energy does an atom exert to keep? Because it's going to take that much or more to get rid of it, right? So ionization energy is the amount of energy that it takes to remove. Another way to think of it is the amount of energy that an atom uses to keep an electron. Electronegativity is the amount of force that the other atom exerts to get. So when the electronegativity is greater than the ionization energy, well, then the electron will move. So if one wants it more than the other one's willing to put into holding it, it transfers. Now, what is the trend on the periodic table for ionization energy? What is a positive trend? Up and to the right. So when you place different elements, if they're in a column, the higher up, the higher the ionization energy, and also the higher the electronegativity. And as you go from left to right, the farther to the right, the greater the ionization energy and the greater the electronegativity. So if you're reading from left to right, they increase to the right. If you're reading from bottom to top, they increase from bottom to top. The opposite trend is with radius, correct? Radius is increasing down and to the left, which means if they're in a column, from top to bottom, they increase. And in a row, from right to left, they increase. Remember, the trend is opposite in that as we're going from top to bottom, the radius gets bigger because as we go down, we're adding electrons to energy levels and we're building out. However, when we move from left to right, We're adding electrons to the same energy levels. We're not building out, think of it as shells. We're not building greater shells. We're adding more electrons to the same shells. And every time we add an electron, we also add a proton in the construction, which means there's a greater pull from the center, and it pulls the electrons in. So as we move from right to left on the periodic table, your nucleus, your radius rather, actually gets smaller as you add electrons across. But it gets larger as you add electrons down. Okay. Again, I think it's easier just to draw the single arrow and say, in terms of radius, down and to the left is a positive trend. For ionization energy and electronegativity, up and to the right is a positive trend. And place everything relative to that. So we've already discussed the three periodic properties of atoms: ionization energy, electronegativity, and atomic radius. What does it mean if it's a periodic property? It's something that repeats, right? It's something that's a trend that you can look here to the periodic table of elements, right? If it's periodic, it means it has a trend to it, it has a routine to it, it has a pattern to it that repeats itself. What's the repeating pattern? Up and to the right is increasing ionization energy, up and to the right is increasing electronegativity, down and to the left is increasing atomic radius. Those are properties that you can put things relative to one another and say, because of this trend, it's true, it's a periodic property. We've already done 11 a couple different times, so we'll skip that. What's the fundamental difference between ionic compounds and covalent compounds? Another way to say that, what's the fundamental difference between ionic bonds and covalent bonds? Covalents share ionics, give and receive. Yeah. They transfer. So think of it as ionics transfer, covalents share. If you have a metal and a nonmetal, the metal is going to give up electrons. The nonmetal is going to receive the electrons. They're going to go to their octets, but now they have opposite charges and they're going to be attracted to one another. Covalents, they get together and they share. And by sharing, they form a relationship. But they don't give up, they share. So they could say, hey, this electron is still mine. I'm just going to let you borrow it once in a while, but it's still mine. And the one that's receiving that electron occasionally says, hey, I didn't have that before, but now I do. It's mine. So they're kind of sharing it. They both see it as belonging to themselves as part of their octet when they share it. So covalents share, ionics transfer. The bond in an ionic is the opposite forces, the opposite charges attracting. That force is the force that holds the molecule together. In covalence, it's the sharing of the electron and the different elements saying, hey, if I break this bond, if I move away from this other atom, I'm giving up an electron. It's going to take more energy for me to go away from them than it is to just stay where I'm at and be satisfied with this relationship. Okay, so I'm going to stay here and share rather than give it up altogether. That's part of the idea behind a covalent. They stay together so that they don't lose what they have. We talked about the formula Mg2O2. What's wrong with that? It's not, you haven't gone through and looked for the least, or the greatest common factor being 2. So it'd be just MgO. Magnesium and oxygen, it's an ionic bond, right? Mg, metal, oxygen, a nonmetal. Okay. Magnesium, as a metal, wants to go to a +2 charge. Oxygen, the nonmetal, wants to go to a -2 charge. If you do the technique of dropping the charges, crossing and writing as transcripts, it would be Mg2O2, but you have to stop and go, wait a minute, that's not the simplest combination. Instead of Mg2O2, it can become MgO, because it has a greatest common factor of 2 for both of them. Divide the 2's by 2, you get 1 each. It is MgO. What gases are involved in the Earth's 3-tiered protection system against high-energy light that comes from the sun? Let's talk about the gamma rays, the highest energy wave. It breaks up what bonded homonuclear diatomic? Nitrogen, because nitrogen has a triple bond. We just saw that in the video as well. Nitrogen has a triple bond. Because it's a triple bond, it takes the highest amount of energy to break it apart. Gamma rays do that. Gammas have enough energy to break up a triple bond. Now, when you have a homonuclear diatomic nitrogen, 3 bonds of holding this nitrogen together, and the gamma hits it, the gamma breaks the bonds. Now what do you have? Two individual atoms of nitrogen, right? Two individual atoms of nitrogen which happen to be right beside each other. Now the gamma ray is completely used up. It's gone. All that energy broke the bond and the gamma is destroyed. So it doesn't come down to fry us. Now you've got two atoms of nitrogen which are in proximity to one another. What are they naturally going to do? Rebond. And so it's an automatic reforming of the protection layer. Gamma hits it, boom, they reform. Gamma hits it, boom, they reform. Gamma hits it, boom, they reform. So it's an automatic self-regenerating protection system from nitrogen that protects us from gamma rays. The next level is ultraviolet rays. Ultraviolets don't have enough energy to break up a triple, but they do have enough energy to break up a double. And the double bond gas that they're going to run into is what? Oxygen. Homonuclear diatomic oxygen. Same principle. The X-rays hit oxygen, break the double bond. Now you have two atoms of oxygen in proximity. What are they naturally going to do? Rebond. X-ray, bond, X-ray, bond, X-ray, bond. And so this, again, self-automatically regenerating protection system is protecting us from the X-rays. Lastly, the third gas, a little bit different than the other two because it was homonuclear nitrogen, homonuclear diatomic oxygen, and the next we have three atoms of oxygen bonded together as ozone. Ozone has two oxygens bonded with a double bond and a third oxygen bonded with a single bond. And again, it's a single bond in that molecule that we're looking for because the next level ray that doesn't have enough energy to break up nitrogen, the triple bond, it doesn't have enough energy to break up oxygen, the double bond, but it does have enough energy to break up the single bond between two of the oxygens in ozone, is the ultraviolet rays. Ultraviolets are deadly, but not as high energy as gamma, not as high energy as X-ray. Ultraviolets will kill skin cells, and it's what you know as a sunburn, okay? So ultraviolet rays, too much of the ultraviolet is deadly, but we still do get some that come through. And part of the deal here is that when you've got ozone, again, you've got a double bonded, I'm not going to draw all the valence electrons, but you've got a double bonded oxygen and a single bonded oxygen. As the UV light comes down, boom, it can break apart that bond. It can break apart the single bond, but not the double bond. It can break this apart. The problem is, this is not an automatically regenerating molecule. If you have ozone and you lose an oxygen, what do you have? You have two single oxygens and a lone third oxygen, right? It doesn't automatically regenerate as ozone. And so ultraviolets do break up ozone, but that broken up ozone needs to be replaced by a new ozone molecule. It can't spontaneously regenerate as ozone, which is why we have the issue of holes in the ozone layer, because ultraviolets that hit ozone do actually consume the ozone, change it into something else that doesn't automatically regenerate. But those are the three gases involved in the three-tier protection system against high energy light. And list the homonuclear diatomics. It was interesting. The question about homonuclear diatomics, several of you wrote down the chemical symbols for the homonuclear diatomics and forgot to put the subscript 2. Isn't that the whole concept of the homonuclear diatomics? Like, what's a homonuclear diatomic? H. No, it's not H. It's H2. Right? Then it's nitrogen, N2, O2, F2, Cl2, Br2, I2, and At2. Those are the homonuclear diatomics. It's kind of ironic that you would write that, for example, chlorine is a homonuclear diatomic with the symbol Cl. Show it's a homonuclear diatomic by putting Cl2. All right? So again, the homonuclear diatomics are H2, N2, O2, and all of column 7. So it forms a 7. That's the way I first remembered it. It's column 7 in the form of a 7 plus hydrogen. So any questions on those review questions? Quick 15-question review. Does it seem like forever ago since we did those? That's one of the problems of doing review questions and practice problems as you go through. If we'd done it like we did before, you probably would have just turned this stuff in Friday, maybe Thursday, and so you'd be remembering more accurately what you wrote down or what you knew and didn't know. That's one of the drawbacks of doing it the way we did it for this module. Let's go ahead with the practice problems, because I think these are more related to some questions that you may have. Real quickly, the Lewis structures for the following atoms: Ge, Te, and barium, Ba. Okay? So we're going to draw the Lewis structures. What is the first thing we need to do? Just determine how many valence electrons they have, right? The germanium, where would we find that? Right over here, right? So it's a column what? Column 4. So carbon, silicon, germanium, right there, column 4. What does the Lewis structure for a column 4A element look like? Column 4A. I sometimes drop the A, but remember, valence, we're looking at the A columns. So column 4A, just 4 dots, one at each cardinal position, cardinal coordinate. Te, 6A. So its valence, its Lewis dot structure is going to look exactly the same as what other elements? Every other element in the column, right? So oxygen, sulfur, they all have 6. 1, 2, 3, 4, 5, 6. Barium, column 2A. 1, 2. As we said before, we can replace any other element in that column with the same Lewis structure. So this is just as valid for Be or Mg or calcium or strontium or radon. Right? They're all column 2A elements, same Lewis structure, just different symbol representing what the actual element is that's under question. Give the chemical formula for the following molecules. Aluminum sulfide. How are we going to go about answering this question? What is the chemical symbol for aluminum sulfide? What's the process? What's our very first step? Find what on the periodic table? The elements that are involved in the molecule, right? So aluminum, Al, okay. Sulfide, it's the ionic form of sulfur. Sulfur is S. Okay. Metal or non-metal? Metal, and so the bond is ionic. Okay, so since it's an ionic bond, now we're going to go to finding out what charge the ion wants to become. What does aluminum want to become? Sulfur. Two negative. So we're going to drop the charges, transpose as subscripts. Greatest common factor? 1. So we're done. It's aluminum sulfide. Second one is iron 1 nitride. Iron 1 nitride. Now, because I see a Roman numeral, what do I know that is? I know it's a metal, right? And what charge is it going to have? Now, the chemical symbol for iron is not I. Okay, and I joked about that before. Many of you did that. Used I for iron. It's not I, it's Fe. Iron is, Latin name is ferrous. And we know by the symbology up here that it wants to become 1 plus. Nitride is the ionic form of nitrogen. It's a metal and a nonmetal. We just validate with that one more time. Metal and a nonmetal, so it's going to be an ionic bond. Nitrogen is a column 5 element, so it wants to go to what form? Ionically, what charge? Negative what? 3 negative. Okay. Dropping the charges, transposing as subscripts, becomes Fe3N. Greatest common factor is 1, and so we're done. C, magnesium oxide. Okay. Magnesium oxide. The two elements involved? Magnesium and oxygen, metals and nonmetals, or both nonmetals? Metal and non, so it's ionic. Charges magnesium wants to go to 2 positive, and oxygen is 2 negative, right? And this is the one we did before, where if we just simply transpose, it would be Mg2O2. Now apply the greatest common factor of 2, so divide by the greatest common factor, becomes MgO, magnesium oxide. Lastly, chromium 3 oxide. We've got chromium, we've got oxygen. Chromium is a metal or nonmetal? Metal charge, this chromium 3 means it wants to become 3 positive. Oxygen, nonmetal, column 6, wants to become 2 negative. So this becomes chromium 2O3, chromium oxide, Cr2O3. Any questions on using or coming up with a chemical formula for ionics? No? Which atom gives up its electrons the most readily? What does that mean? Which one gives up their electrons the most easily, right? In other words, which one is holding on to it the least? Another way of thinking about it, right? Which is describing what? Which of the periodic properties? Ionization energy, right? So we're looking for the lowest ionization energy between aluminum, beryllium, it must be over here. Between aluminum. Okay. So we've got a column 3A elements. These are the 4 in question. Which atom gives up its electrons the easiest? Which one has the lowest ionization energy? Of that column, with the trend, which one is the lowest, the least? IN, right? Because the trend for ionization energy is up and to the right. Up and to the right is greater, therefore down and to the left is lower. So in a column, the lowest one has the lowest ionization energy. Next question. Order the following in terms of increasing ionization energy. SR, SB, and I. So we're going to ignore this one for now. Increasing ionization energy, what's the trend? Looking at these, they're all in column, or excuse me, all in row 5. So again, the ionization energy increases up and increases to the right. Order them in the following, according to increasing ionization energy, it increases from left to right. So increasing would be SR-SBI. Because the trend is increasing up, increasing right, SR-SBI. Which atom has the greatest desire for extra electrons? What's another name for that property? Desire for extra. Electronegativity. How much energy is it going to use to get more? The trend is the same as the ionization energy, right? So which has the greatest desire for, we're using nitrogen, I'll block these ones. N, S, B, we go again. And AS. Again, which atom has the greatest desire for extra? Same trend, and that would be nitrogen. Order the following in terms of increasing atomic radius. Increasing radius, we have potassium. We're going to be in this row. Let me get rid of the extra marks. So we're going to be in row 4. With potassium, let's see, we've got astatine, bromine, and cesium. Is that right? Yeah, right here. So column 4, in terms of increasing radius, what is the trend for radius? It increases left and down. Okay? These are all in the same row, so we're going to look at the trend as being positive to the left. So in terms of increasing, it's going to go BRSEASK in terms of increasing radius, because the trend is increasing to the left and increasing down. Draw the Lewis structure for CH4. Almost from the top, off of top of our heads, right? Carbon. How many unpaired valence electrons does carbon have? 4, right? It's going to become automatic for us because we're going to use carbon in the center so often with 4. And the second part is H's. We got 4 hydrogens. Okay? We've got 4 unbonded single electrons, and we have 4 hydrogens, and hydrogen only has 1. It's looking for 2. And so it's going to end up looking like this. It's going to get its 2 by sharing. 2, 4, 6, 8. All the hydrogens see 2, the carbon sees 8, and it's done. CH4. Lewis structure for PCl3. How many unbonded electrons or unpaired electrons are in chlorine? Just 1. In phosphorus? 3. It's going to be the center. How many chlorines do I have to pair with it? 3. I'm going to orient my unbonded electron in the 3 chlorines. Show that they're shared by changing them with the bond, and there's my PCl3. Your column 5 elements, remember the technique I encourage you to do is always put the bonded pair, or excuse me, the paired electrons on the top, because it tends to be a center element, and put the pair on top, which means you're going to have three forks, 3 spokes to attach to, whereas in column 4 you're going to have 4 spokes to attach to. FNO. Okay? F7N5O6. Pair 'em. 8, 1, 2, 3, 4, 5, 6, 7. Bring it up. Bring it up. There you go. FNO. Let's double check. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Sorry, I'm rushing here at the end, I know, but based on their Lewis structures, which molecule is the easiest to break apart? You've got 3 molecules there. The C2H4, PN, and H2. Which is going to be the easiest to break apart? Okay, the one that has the easiest to break bonds, the single bonds, right? Because singles are easier to break than doubles, and doubles are harder to break than triples. So you're looking for the one that has single bond. Just looking at it real quickly, some of them contain single bonds, but they also contain double bonds. But if you had to pick between these three without drawing anything, without any other information, which one do you know only has one single bond? H2. It is a hydrogen. That's its entire Lewis structure. H bonded to H. One single bond, meaning all it takes is breaking that one bond, and now the whole molecule is dissolved. That's the easiest one to break.